Hello everyone. Good morning. So sorry for a little bit of delay. I was waiting for for the others, but so far we have 22. So I think we can no longer wait. So I will continue with our lecture. Okay. So today I will do lecture first. Then tomorrow I replace the Monday class. So sorry, Monday class I have another event that I cannot avoid. So I have to postpone last Monday class to tomorrow. So tomorrow during our lab time, I will do tutorial. Our lab time is 8:30 to 11:30, but I will start our tutorial at 9 o'clock. So about 9 o'clock until 11. Let's see how. Probably 2 hours. 2 hours of tutorial tomorrow. Okay, so today lecture first. I finishkan lecture chapter 2. Then tomorrow we will do tutorial. For the tutorial question, it's already on Teams. I already shared in the Teams folder as well in the VLE as usual. So as I told you for my tutorial, if you want, you have time to do it earlier, so much better. But if you don't have time, it's very understandable. Just you don't need to prepare. I don't need to prepare. Just come to my tutorial. Hopefully, you have the question with you. You ready with your paper, pen, pencil, and so on. So as I explain, you can at least try to do it together. But of course, it's a bit impossible for me to wait everybody lah. But I will really explain step by step in the tutorial. And what's more important is actually understanding the steps so that you can actually do it on your own. Okay, so that's for tomorrow. For the others, I already released the lab schedule for your laboratory on VLE as well as on Teams folder. So please check the lab schedule. The lab schedule is for those who will come physically. Also, since the members are from different groups, so physically I will combine you guys in the group for the lab physically. But for your lab report and so on, you will still do it you will still do it according to your original group. Okay, just that masa lab tu physical buat you will do according to the physical lab, tapi for your lab report you will do according to your original group. Okay, so next week I will explain on Monday how the lab going to be. So the lab is next week will start. So 2 minggu je. I will take only 2 weeks of your time to do the lab. So week 4 and week 5. Or for those who are not able to attend the lab physically, you are still expected to attend the lab on Teams. So I will do a live demonstration for that 3 hours. So although you are not in the lab physically, you are still expected to be on the Teams for the lab session. So attendance will be recorded as well lah during the lab session on Teams for those who are not able to attend the lab physically. Okay, so just to be fair for those yang dah kena datang fizikal, for those yang tak dapat datang fizikal pun, you have to be on Teams for that 3 hours. I will do a live demo as your friends are doing the lab. Okay, the rest of the detail I will explain next Monday on that matter. Okay, so today I will continue on our lecture. Before I forget, to recap back what we have done last week. So last week we have done a lot of part for chapter 2 already. Okay, so first we have already learned how to derive the design equation for the reactors. So you have derived the design equation for batch reactor, for CSTR, and for PFR. Okay, so 1. Next, we learn how to determine the volume of the reactor, or you already started a very basic understanding of designing the reactor by determining the reactor volume, PFR, CSTR, when you are given this table of information. Okay, the table information will be conversion and your minus RA, rate of disappearance of A, or if the information is converted into the form of Levenspier plot. Okay, so based on these 2 types of information, it's the same information, just that one in the form of table. If it's in the form of table, it's X minus RA, means for every conversion, what is the minus RA? So you use that to calculate the volume of PFR, the volume of CSTR. Or it is converted into a plot. So the plot is 1 per minus RA versus X. So you don't forget that part. Kalau plot dia mesti it will be 1 per minus RA versus X. So using the same plot also, you find the volume of CSTR, the volume of PFR. Okay, so kalau volume of CSTR is very straightforward because CSTR formula dia kan linear formula. Or in a simpler word, in the form of a plot, volume of the reactor, CSTR, is equivalent to the area above and below the curve, the rectangle area. So area above, below the curve is the volume of CSTR. On the other hand, if you are doing PFR, the volume is not no longer straightforward for you to calculate, because the volume of the PFR, plug flow reactor, is equal to the area under the curve. Okay, so kenapa CSTR area above below the curve? Kenapa PFR area under the curve? It's because of the design equation. Okay, sebab ikut design equation dia. So for PFR, because the area under the curve ni dah tak straightforward for us to calculate. So we need to use Simpson's rule, or in more exact, we use Simpson 1/3 rule untuk kira luas di bawah graph, which is equal, luas di bawah curve, the area under the curve, which is equal to the volume of the reactor. Okay, so that's what we did last week. Okay, but what we did on these both reactors are for single reactor, meaning when you're using only one reactor to achieve your desired conversion in your reaction. But as I also told you previously, most often, saya nak pergi kepada ni. Okay, most often it is you would not be able to obtain a high conversion when you're using a single reactor. Okay, so ingat, conversion ni refers to your raw material. So if we always desire the highest conversion possible, which is 100% lah. If you mean 100% conversion, meaning all your raw material, your reactant converted into product. Okay. But rarely it is able to achieve that high conversion in one reactor. Okay, so as I told you before, you have two options. Okay, katakan daripada first reactor tu dah keluar, you have two options. One option, you will come up a mixture of your product and your unconverted reactant. Okay, so first choice, separate, recycle back your reactant. Or second choice, you can flow it to the next reactor continuously. So either PFR pun boleh, CSTR pun boleh, meaning the one that flows from the first reactor directly enters the second reactor. So by doing this, you don't need to separate. So you remove one process, dah tak payah separate, just flow to the next reactor with the hope that when you flow to the next reactor, the unconverted reactant will further react. So when they further react, hope that more of this reactant will be converted into product. Okay, so that's the concept of a continuous process, which I already explained to you last week. Then next, I also explained to you about the conversion. So part conversion ni yang kamu kena betul-betul faham. Conversion is always calculated based on the very original molar flow rate that enters the very first reactor. Maksudnya, katakan you have two reactor. Okay, you have two reactor. Let's say yang masuk reaktor pertama adalah 100 mole per second. Okay, so katakan after the first reactor, 50 mole telah bertindak balas. So baki lagi 50 mole kan? Okay, so 100 yang keluar daripada reaktor pertama adalah 50 mole per saat jugalah. Okay, so conversion dalam reaktor pertama, 100 minus 50, in minus out, divided by the in again. So 100 minus 50 divided by 100, you get 50%. Maksudnya 50% of your A has been converted in the first reactor. Okay, so yang keluar tadi daripada reaktor pertama 50 mol per saat kan. Okay, so this 50 mol per saat akan masuk kepada reaktor yang kedua. Okay, so katakan dalam reaktor kedua ni, from the 50 mol per second, dia further convert, right? So daripada 50 mol per saat ni, katakan dia convert, tinggal sekarang baki menjadi yang keluar daripada reaktor kedua, the one that exits the second reactor, let's say sekarang 25 mol per second. So reaktor kedua yang masuk 50, 100, 50, keluar reaktor kedua jadi 25. Okay, so conversion sekarang macam nak kira. Conversion untuk reaktor kedua, Okay, conversion reactor pertama tadi yang 50% kan, okay, that 50% is X1. Reaktor pertama punya conversion X1, okay, ataupun we call it intermediate conversion. Okay, dan reaktor kedua ada dua reaktor, conversion pada reaktor terakhir kita panggil the final conversion or overall conversion. So overall conversion ni kita nak kira berapa banyak penukaran dia, conversion dia, it will be 100 yang asal masuk tu 100 mol per saat tu tolak minus 25 divided again with 100. So 100 yang masuk asal 100 mol per second minus the one that flowed out from the second reactor. So 100 minus 25 divided by 100, you get the conversion as 75%. So kamu perasan reaktor pertama convert 50%, reaktor kedua convert jadi 75. So means dia meningkat daripada 50% menjadi 75%. Okay, so that's why I keep saying conversion dia tak reset, dia bukan 50% reaktor pertama, tiba-tiba reaktor kedua jadi 25%. Tak, dia akan sentiasa meningkat sebab we calculate based on the original molar flow rate that enters the very first reactor. So naturally your conversion will increase with the number of reactor. Maksudnya X2 bigger than X1. If you have third reactor, X3 bigger than X2. You have the fourth reactor, X4 bigger than X3. Okay, so conversion for all the reactor before the last reactor we call as intermediate conversion. So kalau kita ada 3 reactor, 2 intermediate conversion, X1, X2. The very last reactor conversion we call overall conversion, X3. So kalau 4 reaktor, intermediate conversion X1, X2, X3, final overall conversion X4. So kamu kena ingat X2 bigger than X3, X2 bigger than X1, X3 bigger than X2, X4 bigger than X3. Dia conversion akan meningkat. Okay, so that's on conversion. I already explained on the conversion for reactor in series. Okay, now next. To understand the volume of the reactor. Okay, kamu kena faham. Okay, we want to calculate previously we calculated the volume for single reactor to achieve the desired conversion. Okay, so we are going to do the same one when we have reactor in series. Okay, so kamu kena faham konsep dia adalah reactor punya volume ni is depending on again conversion and the molar flow rate. Okay, so we have to calculate volume dia tak semestinya akan sama. We can calculate the volume of the reactor for reactor 1, reactor 2, reactor 3. Okay, depending on basically on your conversion. So from the conversion tu kita akan kira volume reactor dia. Okay, so now the calculation become complex sebab you have actually learned the CSTR punya formula. Tapi sekarang formula ni yang kamu belajar tu adalah untuk single CSTR. Now when we have reactor in series, the formula will have to be modified. Konsep dia masih sama, principle dia masih sama, tapi the formula will need to be modified according to the arrangement or according to the susunan reactor tu in the system, in the series. Okay, so for me to better explain it, let me show you one by one. Okay, first of all, let's see now. You see first for the single CSTR, one CSTR, formula dia, volume CSTR equals to FA0, okay, the one that enters the first reactor, minus FA, the molar flow rate that exits the reactor. FA0 is the initial molar flow rate. FA is the final molar flow rate or the exiting molar flow rate per minus RA. Done. Okay. So again, as I told you guys, sebab when we talk about reactor design, it's always in the form of conversion. Okay. So kita kena perkenalkan conversion in the formula. Okay. So how do we introduce that? You know that susunan formula dia FA, basically from the formula X equals to FA0 minus FA per FA0, in minus out per in. When you rearrange the formula, FA ni sama dengan FA0 in bracket 1 minus X. Okay, so if you forget, we have learned before this. Conversion, kita boleh tulis sebagai FA equals to FA naught 1 minus X. So now I replace the FA with FA naught 1 minus X. So you see the FA naught is still in front because the FA is equals to FA naught 1 minus X in bracket. So you minus it, okay, per minus RA. Then when you rearrange back, you will get the formula as FA naught X per minus RA. Yang ni kita dah pernah buat untuk single reactor. Okay, so this is nothing new. This is what you have learned for single reactor. Formula untuk cari volume dia is equal FA naught X per minus RA. Okay, now I want to do for reactor in series. So part ni yang kamu kena faham. Kita kena faham single, baru kita boleh faham macam mana kita nak buat untuk reactor in series. Okay, so for reactor in series, right, so now you imagine I have two CSTR in series. So the initial molar flow rate that enters the first reactor is FA naught. The one that exits the first reactor is FA1. Okay, saya akan ingat. FA1 sama dengan FA naught in bracket 1 minus X1. Ni yang kita belajar last week. I already taught you, right, how to express the conversion. Okay, so jadi FA1 sama dengan FA0 1 minus X1. Ataupun erti kata lain, kalau kita nak tahu molar flow rate yang keluar daripada reaktor yang pertama sama dengan initial molar flow rate in bracket 1 minus the conversion in the first reactor. So maksudnya dalam reaktor pertama, dia akan convert daripada 0 kepada X1. Okay, daripada 0% to, let's say X1 ni adalah 0.6, 60%. So they're converting from 0 to 60%. Okay, so that's first reactor. So the one FA1 will be the initial, will be the molar flow rate that enters the second reactor. Yang keluar FA2. So conversion dia, FA2, the FA2 is equals to FA0 in bracket now is 1 minus X2. Sebab kita nak kira FA2 ni daripada reaktor kedua kan. So, kenapa FA0? Sebab saya kata dia mesti kira berdasarkan initial molar flow rate yang asal yang masuk tu. Sebab tu masih FA0 tetapi now in the bracket become 1 minus X2 because we are talking about FA2 in the second reactor. So, let's say reaktor kedua, the conversion is 80%. So, what does this mean? Meaning, the conversion from first reactor, 60%, they further converted the A now become 80%. So reaktor pertama only 60% A converted. Reaktor kedua now become 80% of A converted. You can see the conversion increases. Okay, you understand that? Now we talk about the design of the reactor, how to calculate the volume. So the volume of the first CSTR, so penyiraan volume untuk volume pertama, volume kedua ni dah jadi berbeza. So you have to understand the reactor volume can be different. Although you arrange in series, the reactor volume can be different, or I would say easiest word, the required volume can be different. Okay, so reactor pertama, volume dia become FA0 enters the first reactor molar flow rate minus FA1, the molar flow rate that exits the second reactor, divided by minus RA1. Kenapa minus RA1? First, sebab dia berlaku dalam reaktor pertama. Kedua, minus RA1 ni depends on X1. So, kamu kena specify minus RA ni 1 ke 2. Sebab kalau minus RA1, it depends on X1. Kalau minus RA2 bergantung kepada X2. So, clearly state minus RA1, RA2. I want to calculate for the first reactor. That's why it's minus RA1. Done. Okay, next step. Sama je. Kita dalam reaktor ni, mungkin you might wonder why do we need to always rearrange ke, wujudkan ke, sebab dalam reactor design ni mesti it's always about conversion. We always want to know how much how much A is converted, how much your raw material is converted. So kalau equation tu tak ada X memang tak boleh, kena ada X dalam equation. Sebab tu we express FA1 in the form of conversion. Dia menjadi FA0 1 minus X1. So I replace my FA1 with FA0 in bracket 1 minus X1. Sorry. Divided again by minus RA1. You will eventually get the volume of the reactor 1. Okay, volume of the reactor 1 become Ni kamu kena rearrange. So kalau a little bit of mathematics lah. But if you realize, it become, kita buka, we open the bracket, FA0 minus FA0 plus FA0 x1. That's why eventually you get it as FA0 x1 per minus RA1. So that is how you calculate the volume for the first reactor. Okay, some of you might realize bukan sama ke dengan single reactor? Yes, for the volume of the first reactor in series is quite similar untuk volume reactor single reactor. The only difference is kita dah label X2 sebagai X1. Very important because if you just say X dalam reaktor bersiri, it can be X1, it can be X2, it can be X3, so on and so forth. So you have to specify. If you say X1 means conversion dalam reaktor yang pertama. First, second, even the minus RA. Sekarang kita dah tulis minus RA1 because minus RA tu kena ikut X. Kalau X1, minus RA1. Kalau X2, minus RA2, so on and so forth. Okay, so it looks similar. It is quite similar. Just that make sure you understand it applies to the very first reactor, X1 minus RA1. Okay, so biasanya reaktor pertama, student takkan ada masalah untuk kira sebab dia faham hampir sama dengan single reactor. It become confusion bila jadi reaktor kedua, reaktor ketiga. Okay, kenapa? Okay, let's see back equation dia untuk derive volume reactor yang kedua. Okay, so imagine now I have the second reactor in series. I want to calculate the volume. Sorry. So the volume in the second CSTR. So now you see I will write it as VCSTR2, volume reactor kedua. VCSTR1, volume reactor pertama. Okay, so volume CSTR2 equals to yang masuk kepada reaktor kedua adalah FA1. Dah lain kan tadi reaktor pertama yang masuk FA0. Reaktor kedua yang masuk adalah FA1 minus the one that exits the second reactor FA2. So FA2. So become FA1 minus FA2 per minus RA2. Okay, yang ni part yang selalu student kadang-kadang terconfused. When we talk about second reactor, dia mesti minus RA2, iaitu the rate of reaction at my second reactor conversion, X2. Okay, so minus RA2. However, this equation again doesn't have X. Kita tak boleh. Kita mesti dalam equation tu dalam bentuk X perkiraan dia. So, kita dah tahu FA1 sama dengan FA0 in bracket 1 minus X1. For the second reactor, FA2 sama dengan FA0 in bracket 1 minus X2. So, I replace my FA1 with FA0 1 minus X1. FA2 with FA0 1 minus X2. So both kamu kena ganti dengan equation conversion. That's why I taught you about the conversion punya formula. Sebab you have to understand the conversion formula, then only we can derive the design equation for CSTR. Okay, so now this one you rearrange as well. You open the bracket, you rearrange the equation. You basically get the volume of the second CSTR as FA0 in bracket X2 minus X1 per minus RA2. So this is to calculate the reactor volume for the second reactor. Okay. Now, katakanlah we want to design, we have the third reactor. Katakan kita sambung kepada reaktor ketiga, what will be the volume? So basically kamu dah boleh agak. Okay, kalau volume reaktor kedua, FA0 in bracket X2 minus X1 per minus RA2. Therefore, if I have the third CSTR, the volume will be VCSTR3 equals to FA0 in bracket X3 minus X2 over minus RA3. Itu kalau reaktor ketiga. Okay, kalau reaktor keempat, volume CSTR for the fourth reactor equals to FA0 X4 minus X3 over minus RA4. Maksudnya, erti kata lain, in the first reactor, kalau kamu perasan sebenarnya ada trend dia. Dalam reaktor pertama, dia convert daripada 0 to X1. Sebab tu kamu nampak ada FA0. Technically, kalau kamu perasan, is volume CSTR pertama, the first CSTR volume is FA0 in bracket X1 minus 0. Tapi minus 0 tak payah tuliskan, that's why they leave it as X1. Tapi technically it's bracket X1 minus 0 sebab dia convert daripada 0 to X1. Satu X1 minus 0. No minus 0 become X1. Reaktor kedua convert daripada X1 to X2. That's why become X2 minus X1. Reaktor ketiga convert daripada X2 to X3. So X3 minus X2. Okay. Second thing, let's say sekarang kamu confused ataupun kamu terlupa X2 tolak X1 ke X1 tolak X2 ataupun kalau reaktor ketiga X3 minus X2 ke X2 minus X3. Always remember conversion will increase with reactor. Maksudnya katakanlah reaktor kedua ni X2 will always be bigger than X1 sebab conversion meningkat. So means like I told you right, conversion daripada reaktor pertama daripada 0 to 50%. X2 50% to 70%. So means X1 0.5, X2 0.7. So katakan formula ni kamu dah lupa X2 minus X1 ke X1 minus X2 sebab kadang kita we get confused right? Because I always tell you dia meningkat daripada X1 ke X2. Tapi kenapa dalam conversion X2 tolak X1? Okay, senang je. Fikir je logik. As I told you, conversion will always increase. Maknanya X2 will be bigger than X1. X3 bigger than X2. Okay, so katakan sini X2 minus X1. Katakan kamu confused lah kan? Kamu letak X1 minus X2. Okay, so kamu tahu kalau kamu letak X1 minus X2, katakan X1 kamu contoh dia 0.6, X2 kamu 0.8. So if you put 0.6 minus 0.8, you get a negative for sure. So fikir balik logik. Volume reactor tak mungkin negative. You cannot get a negative for a volume of a reactor. So that's how kadang-kadang logic plays a part in engineering. You know logically volume reactor takkan negative. You cannot get a negative reactor volume. So bila kamu kira dapat negatif, kamu dah tahu logically volume reactor can never be negative. So you recheck your calculation. There is a part that definitely that you made a mistake. So this is a way for you to check. Sebab kalau kamu letak X1 tolak X2, confirm jawapan negatif, confirm salah. So kamu switch je lah, letaklah balik X2 minus X1. So most likely, definitely get a positive answer and definitely that's the right answer. Okay, so that's one way because sometimes student will and may get confused during test atau exam. Dia lupa ataupun dia keliru X1 tolak X2 ke X2 tolak X1 ataupun X3 tolak X2 ke X2 tolak X3. Kalau kamu dapat jawapan negatif, kamu switch je lah. Memang confirm jawapan tu salah sebab volume reactor tak mungkin negatif. Okay, so that's one part on understanding the reactor volume. Okay, alright. So for you to understand better, let me try a question together. Okay, so let me try this question. Okay, so katakan the reaction A produce B is carried out in a single CSTR and 2 CSTR in series. Okay, reaction yang sama kita jalankan dalam satu single reactor ataupun dua reactor in series. Both are CSTR. Species A enter the reactor at the rate of 0.4 mole per second. Okay, at this moment kamu dah kena tahu nilai itu adalah apa based on the unit. Okay, sebab saya kata kamu dalam engineering dia jarang kata okay, molar flow rate, concentration, number of moles, volumetric flow rate. Dia tak cakap directly. Kamu kena tahu daripada melihat unit dia. Okay, so in this case, the first cuba digest ayat tu dulu. Species A enters the reactor. So when you see the word enters, kamu tahu ni adalah initial rate. Okay, tak kisahlah volumetric flow rate ke, molar flow rate ke, kamu tak sure lagi kan. Tapi kamu tahu dia mesti initial. Not, dia mesti ada not. Okay, next. Tengok unit dia, mole per second. So let's say kamu kadang-kadang kamu confuse unit. Kamu tukar unit itu per dimension. Kalau mole, dimension dia mole. Second dimension dia time. Okay, second tu unit, dimension tu time. So mole per time, kamu tahu tu adalah molar flow rate. Mole per time kan molar flow rate. So kami ingatkan molar flow rate ada dua kan, initial molar flow rate ke final molar flow rate. So since dia kata enters the reactor, so this is initial molar flow rate. Dia ada kata ini untuk species A. So dia jadi FA0 0.4. So kamu tengok, kamu daripada satu ayat tu kamu kena pandai digest yang 0.4 mole per second ni adalah FA0. So let's say kamu salah, you wrongly interpreted. Let's say you think this is CA0. You think this is epsilon naught, or you think this is volume, means seluruh pengiraan tu dah salah pada line yang pertama soalan. So that's the danger of, not danger, that's the risk, not the risk also. That's the challenge of engineering question, interpreting information. If you wrongly interpreted, you might be wrong at the very first line and the entire question tu jadi kosong sebab salah interpret satu information. And this is not only for exam or not to punish students, but you must understand in the real working world as well. So imagine, let's say you're working in a plant, so you ask your technician to supply you information. So let's say your technician say, boss, flow rate dia 0.4 mol per second. That's your information from your technician, let's say. And you are unable to digest it correctly. Katakan kamu ingat 0.4 mol per second ni adalah concentration, habislah the entire thing. So it's the same applicable even in this course as well. Interpreting information accurately based on the sentence or based on communication. Okay, so first establish kan FA naught 0.4. Okay, next. For the two CSTR connected in series, 40% is achieved in the first reactor. So dia kata untuk reaktor yang dua tu connected in series tu, kita ada dua sistem, satu single reactor, satu lagi dua reactor in series. Kalau dua reaktor dalam series tu, the first reactor dia achieve 40% conversion dulu. Means daripada 0%, dalam reaktor pertama dia menjadi 40% A yang converted. Okay, so far that's the information. Means your X1 0.4. Okay, X1 0.4 dalam dua reaktor series. Reaktor pertama 0.4, X1 0.4. Next, what is the volume of the two reactors to achieve 70% overall conversion? Okay, dia tanya sekarang untuk reaktor yang kedua yang series tu X1 0.4, right? X2 sekarang adalah 0.7. So dia suruh kita kira volume reaktor pertama, volume reaktor kedua. Means berapa besar reaktor volume saya untuk mencapai conversion X1 0.4 dan berapa besar volume reaktor kedua kalau final conversion tu, overall conversion tu 0.7. Means how big my second reactor will be if I want to further convert from 0.4 to 0.7. Okay, that's the question. Means kamu kena kira dua volume reactor tu lah. Okay, next part of the question. Subsequently, calculate single CSTR to achieve the same overall conversion 70%. Okay, so part yang seterusnya soalan ni kata untuk reaktor yang single tu terus capai 70%. Dia tanya berapa besar reaktor volume tu. So you understand this question dia adalah dua dilema. Dilema pertama, kalau saya nak guna dua reaktor dalam series, di mana reaktor pertama 0.4, the second reactor 0.7, what is my volume for both reactor? Or let's say I just want to use one reactor terus achieve 70%. How big that reactor will be? Okay, so you have to calculate basically 3 reactor volume, 2 yang berseries, 1 for the single reactor. Okay, now the thing is that hold on, I have a very important phone call. I'll come back in 1 second. Right, sorry, back to the question. Okay, so done on what the question wants. Okay, so the information further, they give us the table of information. So table, this is very important because the table provide us with the minus RA for each of the conversion. So maknanya at 0%, how much is our minus RA? At 10%, so on and so forth. So using this table, we want to solve the problem. Okay, so let me go to first part. Okay, katakan kita nak kira untuk the single reactor first. Okay, so the single reactor from 0% straight away to 70% in the one reactor only. So how big is my reactor? So the formula volume CSTR equals to FA naught, which is 0.4 as we mentioned, X 0.7. Again, when your numbers are given in percentage, calculation tukar dalam bentuk fraction. So I have to keep repeating this because sebab apa? Sebab every semester will have at least 10 to 20% student who did not convert the percentage to fraction. So kamu kena ingat, part tu memang kamu kena convert kepada fraction. Sebab every semester memang akan ada 10 to 20% of students who do this error. So I have to keep repeat. Dapat percentage, tukar dalam bentuk fraction untuk pengiraan. Okay, so 70% become 0.7. So kalau dalam bentuk fraction, conversion tu dah tak ada unit, is dimensionless. Tak ada unit, tak ada dimension. So X tu 0.7. Okay, divided by minus RA. So minus RA ini adalah at your X. So when my X is 0.7, my minus RA is 0.12. So you replace your minus RA 0.12. The unit is mole per dm cube second. As I told you, it's good to have a good practice of cancelling the unit so that you can check whether your calculation is right or wrong. So your mole can be cancelled, your second can be cancelled. This dm cube, kalau kamu ingat matematik, A per B per C, yang C tu naik ke atas. The third layer will go to the top. So now dm cube ni akan pergi ke atas. So you get your final unit is dm cube, which is correct lah, because I want to calculate volume. The volume unit shall be dm cube ataupun liter ataupun feet cube. So when you recalculate the number, you will get 2.33 dm cube. Apakah maksud dia? Maksud dia, if I want to convert 70% of my A using one reactor, the volume of the reactor must be 2.33 dm cube. Okay, then I will get 70% conversion. Okay, now next, let me calculate kalau kita guna two reactor in series pula. How big my reactor will be? Reaktor pertama, reaktor kedua. Okay, so for the first reactor, dia convert daripada 0 to 40%. Okay, so X1 0.4. So the formula become volume CSTR first equals to FA0 0.4, X1 0.4. Okay, kebetulan molar flow rate pun sama, conversion pun sama 0.4 divided by minus RA1, meaning minus RA at your X1. So your X1 0.4, your minus RA is 0.32. So you divide by 0.32, you get your first volume of the reactor VCSTR1 as 0.5 dm cube, meaning, okay, reaktor pertama, kalau if you want to achieve 40% conversion, you need your reactor volume to be at least 0.5 dm cube. Okay. What about the second reactor? Second reactor sekarang nak convert daripada berapa? 0.4, 40% to 70%. Okay, so the second reactor volume CSTR2 equals to FA0 in bracket is now X2 minus X1 per minus RA2. Okay, maknanya minus RA apabila your X2. Okay, so FA0 0.4, X2 0.7, X1 0.4. So 0.7 minus 0.4 divided by minus RA at X2. So pada 0.7, your X2, your minus RA is 0.12. So you divide by 0.12, you get the volume as 1 dm cube. Maksudnya, untuk reaktor kedua, volume reaktor yang kamu perlukan adalah sebenarnya 1 dm cube if you want to convert from 40% to 70%. Okay. Now, this is something that is very interesting. Kalau kamu perasan, okay, let's convert this into a Levenspiel plot. It will be better discussion if you convert information tadi dalam bentuk Levenspiel plot. Kita kaji Levenspiel plot tu. Sebab kami ingatkan Levenspiel plot, dia convertkan daripada, dia plot daripada 1 per minus RA versus X. Data yang table tadi ni, data table X per minus RA, kita convert yang minus RA menjadi 1 per minus RA and I plot the Levenspiel plot. Okay. Kalau kamu perasan, for the single reactor on my right hand side, on the single reactor, the volume that you calculated 2.33 dm cube is basically the area of this rectangle, kan? Area above below the curve, 2.33, luas kawasan ini. Okay. But kalau kamu pergi kepada dua reaktor in series, okay, kamu kena ingat, berapakah sebenarnya volume yang what was the volume that you calculated? So the first volume that you calculated was 0.5 dm cube, right? So the 0.5 dm cube is the area of this first rectangle. Daripada conversion 0 kepada 0.4, area yang kamu kira 0.5, volume yang kamu kira 0.5 is this rectangle area. Volume kedua yang kamu kira yang 1 dm cube is the area of the second part of the conversion, which is from 0.4 to 0.7. Luas segi 4 ni adalah bersamaan dengan 1 dm cube. So kalau kamu perasan, technically, if the reactor in series, if I total the number of volume is just 0.5 plus 1, 1.5. Kamu perasan, kalau saya guna dua reaktor berseries, jumlah total volume dia hanya 1.5 dm cube. In comparison, kalau saya guna one single CSTR untuk mencapai conversion yang sama, volume dia adalah 2.33. If you realize, both achieve the same overall conversion. Just that one I use single CSTR, another one I use two CSTR in series. But the total volume is not equal. One, because kamu boleh tengok direct, you can see it obviously kan, sebab kenapa untuk two reactor in series total volume dia smaller, sebab luas yang kita kira tu dah berlainan compare dengan single. One. Second, what's the impact of this? So you might wonder, apa impact nak tahu benda ni? Do you realise kalau saya nak guna satu reaktor, saya perlukan volume reaktor tu sebesar 2.33. I can run the same reaction, mencapai same conversion in two smaller reactor. That's the one that I wanted to highlight. You can actually run the same thing rather than using one single reactor. You can actually break it down into two smaller reactor and you still achieve the same outcome with the same conversion. Okay. Now, next implication. Why this is important to know? Okay. Now you have to think back in a very practical perspective. So let's say you're working in a chemical plant, and let's say now, as I told you, let's say sekarang you have a new, let's say you have you want to run this experiment, you want to run this reaction. Okay, and your targeted conversion is 70%. Okay, so let's see you check. Okay, you know that if I want to use a single CSTR, I need the volume of the reactor. Besar volume reactor tu mesti sekurang-kurangnya 2.33. Okay, let's say your superior says we are not buying new reactor. You have to make do with the existing reactor. Means kamu tak boleh beli reactor, kamu kena make do dengan apa yang ada. So you go and check your plant. There are no existing reactor. Let's say there are no existing reactor dengan volume 2.33 ni. Okay, so if you don't have the knowledge, you will think, okay lah, tak boleh run lah. Saya tak ada reactor volume 2.33 ni, memang tak boleh run lah. But instead, katakan in your plant, you have smaller reactors. Katakan kamu ada reactor yang lain, tapi volume yang lebih kecil. So by right, technically, you can actually run the reaction. You can still run the reaction using the smaller reactor. Meaning, sekurang-kurangnya reaktor pertama kamu at least must be at least 0.5 dm cube. And if you have the second reactor of at least 1 dm cube, you connected it in series, you can already run the reaction in your plant. Okay, so that's another alternative yang that you need to know why this knowledge is important in the design of reactor. Not necessarily you need to use one large reactor. You can actually run the same reaction, getting the same overall conversion if you break it down into two smaller reactors connected in series. Okay, so that's what actually this lesson actually teach you about why we learn reactor in series. Okay, so done on the CSTR. So CSTR is senang. Okay, always yang susah adalah PFR. So I always have problem explaining PFR punya volume kepada student because now PFR dia dah bukan straightforward. We are using Simpson 1/3 rule and you have to really understand how to calculate the volume. Okay. Before I will go to the first single PFR dulu. You have to understand the single one. You can understand the series one better. Okay, so single one I already taught you, but I will recap how to find the volume. Okay, so the volume of PFR for a single PFR is equal to FA0 integrating from 0 to X. Ingat, upper limit, bottom limit ni sangat penting untuk PFR sebab nanti penyiraan dia sangat really depends on your bottom limit, lower limit and upper limit. So why the lower limit is 0? Because single CSTR, the initial conversion adalah 0. It starts from 0. X, the upper limit is X because that's the final conversion the reactor will achieve. So 0x dx per minus RA. As I told you kan, integral equation ni, we found that it's equal to the area under the curve of the level sphere plot. Hence, the integral part is then elucidated in the form of Simpson one-third rule. Kita guna formula Simpson one-third rule untuk mencari yang luas di bawah graf, which is equivalent to the integral part of the equation. So, it become Fe0 in bracket delta x per 3. Okay, so delta x ni, I told you right? I will explain kejap lagi. I explain the back part first. Dah pernah explain tapi saya recap balik. At the back part, you have 3 parts sebab Simpson one-third rule. So you have 3 points. So the first point will be 1 per minus RA at your lower limit, which is 0. So minus RA apabila X saya kosong. This is not to signify multiply X. This is to signify minus RA when my X is 0. Plus, okay, 4 tu Simpson one-third rule. Nombor 4 tu ada sebab itu dah Simpson one-third rule. 4 over minus RA at my middle conversion. So middle conversion tu kamu kena cari. Okay, apa maksudnya middle conversion? You will divide your, did the 3 points, right? So your first point is 0. Your last point is your final conversion. So the middle point is the middle conversion between 0 to your final conversion. So let's say your conversion is 80%, 0.8. So 0 to 0.8, your middle x will be 0.4. So maksudnya it will be 4 per minus RA when your x is 0.4. Ataupun pada x middle conversion kamu, which kamu kena cari sendiri. Kamu kena tahu berapakah kamu punya middle conversion. Cari di titik tengah. Katakan conversion kamu 0.6. So 0 to 0.6, middle conversion kamu 0.3. Maka kamu akan mencari 4 over minus RA when my x 0.3. Done. Plus yang belakang 1 per minus RA at your upper limit. Your upper limit is x. So minus RA at your x. Kalau x kamu 0.8, minus RA when my x 0.8. Katakan x kamu 0.6, minus RA when my x is 0.6. Done. Okay, tu part tu senang. Okay, now I explain for PFR in series. Okay, so PFR dalam bersiri ni, untuk reaktor pertama memang senang nak explain sebab for the first reactor, it's very similar to the single reactor. Sama macam CSTR. Kalau first reactor tu berseries, formula dia hampir sama dengan single. So normally dalam reactor pertama, student tak akan confused. Student will get confused the next reactor. Okay, but I explain first the first reactor as well. Okay, dalam first reactor PFR, konsep masih sama. Dalam first reactor, dia convert daripada 0 kepada X1. Kalau tadi single 0 to X, right? But now, dalam reaktor berseries, sama konsep. You have to differentiate. X ni ada banyak. X1, X2, X3, X4. So, kalau reaktor pertama daripada 0 to X1, kamu kena specify 0 to X1. So, formula dia menjadi volume PFR first. So, bila kamu nak kira volume bersiri ni, kamu kena tengok. Kamu kira reaktor pertama ke, reaktor kedua ke, so on and so forth. You have to specify in your calculation. Volume PFR 1 equals to FA0. Masih sama. Masih lagi FA0 di hadapan. But now become integrating 0 to X1 dx per minus RE. Sama konsep, kita kena juga guna Simpson one-third rule. So, FE0 in bracket delta X per 3. Saya lupa nak explain pasal delta X. Apa, nanti kejap lagi saya explain. Sama je konsep dia. Delta X per 3 in bracket 3 point. So, become 1 per minus RA at my lower limit X0. So, apabila X saya kosong, berapa minus RA dia? Plus 4 per minus RA at my middle conversion. Sama konsep. Plus 1 per minus RA at my X1. Okay, katakan X1 kamu 0.8. So, X1 minus RA when my X 0.8. Okay. Part ni okay. Data pertama memang senang. Okay, next. Delta X. I forget to explain about the delta X. So, dalam formula dia, delta X per 3. So, kenapa per 3? One-third rule. Sebab tu bahagi dengan 3. Next, delta X. Delta X is the, kalau kamu belajar dalam mathematics, delta means gap. Ataupun masuk dalam bahasa Melayu kita panggil julat. I think julat is the easiest way to understand dah. Julat ataupun the gap. So the gap tu gap apa? Is the difference or the gap or the julat between the initial x to your middle x or atau your middle x to your final x. So contohnya katakan your initial x is 0, okay. Katakan your final x is 0.8. Hence your middle x 0.4 kan? 0, 0.8, middle x 0.4. Delta x is 0.4 minus 0, which is 0.4, or 0.8 minus 0.4, masih 0.4. So your delta x is 0.4. So again, I emphasize delta x is not your middle x. Just that case kalau memang betul, kalau x kamu bermula daripada kosong, memang delta x tu sama dengan middle x. Memang akan berlaku kalau x kamu kosong. Which is kalau single reactor and first reactor in series memang betul. Tetapi delta x ni takkan sama dengan middle x for the second reactor. So let me explain for the second and so on, baru kamu faham konsep ni. Sebab kenapa I keep repeating? Sebab again, I always try to rely on experience of previous semester supaya you don't repeat the same mistake. Okay. I go to the second reactor, you can understand better. Okay. Dalam second reactor, PFR, they are now converting from X1 to X2. Kamu kena ingat, conversion tak reset kan? So, daripada reaktor kedua ni, dia akan convert, dia akan sambung convert daripada X1 to X2. That's why the formula become volume PFR2 equals to FA0 integrating from X1 to X2. Ni yang berubah sekarang. Sebab reaktor kedua, dia punya lower limit is X1. The upper limit is X2. Kita tak start dengan kosong balik. Kita start terus dengan X1 dalam reaktor kedua. So katakan dalam reaktor ketiga, X2 to X3. Reaktor keempat, X3 to X4. Okay, so kamu have to understand that part. dx per minus RE. So what happens to the formula? So become FA0. Delta x per 3 ni I explain later. I explain the back first. So it become 1 per minus RE at your lower limit, which is X1. So sekarang menjadi 1 per minus RE at my X1. Okay, saya pergi ke belakang pula. Baru saya explain tengah. Become belakang jadi 1 per minus RE at your upper limit, which is X2. Dan tengah-tengah menjadi 4 per minus RE at your middle x. So sekarang middle x ni yang mana? Middle x adalah the middle between x1 and x2. Okay, contohnya katakan your x1 is 0.6. X2 0.8. Maksudnya data kedua dia convert daripada 0.6 ke jadi 0.8. 60% to 80%. So 0.6, 0.8. Middle x dia is actually 0.7. So sekarang dia akan menjadi 4 per minus RE when my x 0.7. So selalu tempat yang part tengah-tengah ni yang student will have confusion macam mana nak cari nilai x middle ni. So kamu kena tahu dia adalah middle x between initial to final. Kalau initial saya 0.6, final saya 0.8, middle dia 0.7. Okay. Now come to the next part, delta x. Part ni yang student akan get confused. Okay. Now, what will be the delta x value? So, tadi kita ada 0.6, 0.7, 0.8 kan? So, delta x is between first x to the middle x or middle x to the final x. So, let's say now my initial x 0.6, my middle x 0.7, hence my delta x is 0.1. Sebab 0.7 minus 0.6, 0.1. Sama, katakan kamu kira kat part belakang. 0.7 to 0.8, berapa julat dia? Still 0.1 because 0.8 tolak 0.7 ataupun julat dia masih 0.1. So in that case, your delta x is 0.1. Don't forget divide by 3. So now I hope you understand kenapa saya keep saying delta x is not your middle x. Kalau start dengan kosong, yes, delta x tu sama dengan middle x. Tapi delta x tu bukan middle x. Sebab bila ada case di mana reactor in series and you no longer start from 0, you will get the confusion yang bukan sebenarnya sama delta x tu. Okay? But again, if you get a little bit not too sure, I will explain in terms of question. But the one that I explained to you just now, you can see in the form of this part. So, tadi saya explain dalam bentuk nombor tu. Dalam slide ni saya dah tunjuk bagaimana kita nak mengira delta x. Yang tadi saya kata 0.1 yang ni. So you can see, right, x1 0.6, x2 0.8, so middle x dia 0.7. So dia punya gap tu 0.1. Kamu kira depan, kamu kira belakang pun delta x dia masih sama, which is 0.1. Okay, so let me try to do it in the form of question because it's always easier to explain when you have question. Okay, so let's say the question, the reaction carry out in a single PFR and 2 PFR in series. So kalau kamu perasan soalan ni sama je soalan tadi, tapi tadi tu CSTR, this is PFR. So I have one single PFR or I have 2 PFR in series. Okay, then next, the species A enters the reactor rate 0.4 mole per second. So FA0 pun still sama macam soalan tadi, 0.4 mole per second. So FA0 saya tak terang lah sebab tadi saya dah explain kan how we come to the conclusion FA0 is 0.4. Okay, done. For the two PFR connected in series, 40% conversion is achieved. So sama konsep macam tadi, yang soalan yang tadi. If I have the two PFR in series, the first PFR to achieve conversion 0.4, x1 to 0.4 ataupun in easy word, dalam dua reaktor berseries tu, in the first PFR, dia daripada 0% dia dah capai kepada 40% conversion, 40% conversion in the first reactor. X1 0.4. Dia kata volume of the two reactor, dia ask us to find the volume of the PFR in series, PFR1, PFR2, if second PFR2 capai overall conversion 0.7, meaning x1 0.4, x2 0.7. Okay, next one, dia ask us to calculate single PFR. So kalau saya guna satu PFR, saya terus capai 0.7, berapa volume dia? Okay, so this is also interesting question. Kita nak tengok balik, nak guna dua reaktor ataupun nak guna satu reaktor, capai conversion yang sama. Okay, the table information is still the same table of information given to us. So kamu kena faham. Okay, ni pun saya kena betul-betul faham for student. Okay, information conversion versus minus RA ni dia takkan berubah mengikut reaktor tau. Ni adalah information ni berdasarkan reaction. We will use this reaction information to determine our reactor design. Means kalau saya nak design reaktor berlainan, information dalam table ni takkan berubah. Yang akan berubah hanya penyiraan design reaktor saya, but this X and minus RA will not change because they are based on the reaction, not the reactor. Okay, so let us calculate the volume of the first, kalau menggunakan two reactor in series. Okay, so we calculate the volume of the first reactor first. So for the first reactor, volume PFR1 equals to FA0 integrating from 0 to 0.4. So lower limit 0, upper limit 0.4 because first reactor convert from 0 to 0.4. Dx per minus RA. So then we convert into the form of Simpson one-third rule, FA0 delta X over 3 in bracket 1 per minus RA when my X is 0 plus 4 per minus RA when my X is 0.2. Macam mana dapat 0.2? Again, kalau kamu tak faham, kamu tengok initial 0, lower limit 0, upper limit 0.4. So your middle X will be 0.2. That's why dia jadi 4 per minus RA when my X 0.2 plus 1 per minus RA when my X 0.4 upper limit. Okay, so yang 141 tu kamu jangan lupa because that's the formula that's required. Okay, next delta X. So how to find delta X? So again, antara 0 to 0.2 or 0.2 to 0.4 between my initial to middle or middle to final, the gap. Okay, so the gap between initial to middle X from 0 to 0.2, the difference is 0.2. Belakang pun sama, from 0.2 to 0.4, your difference is still 0.2. That's why your delta X is 0.2 divided by 3. FA0 0.4. Okay, then yang belakang, okay, when my X is 0, my minus RA is 0.45. When my minus RA is 0.2, my minus RA is 0.42. When my X is 0.4, my minus RA is 0.32. So you calculate this, you formula, substitute into the formula, you get the volume of the first PFR as 0.4, meaning for a PFR, if I want to convert in my first reactor only 40%, the volume of the reactor that I need is actually 0.4 dm cube. Done for the first reactor. So we go to the second reactor. So second reactor ni yang kita a bit get confused at times. Okay. So for the second reactor, we are converting from X1 0.4 to X2 0.7. So lower limit 0.4, upper limit 0.7. So we convert into Simpson one-third rule, FA0 delta X per 3. Okay, let's us now find first how to find delta X. So initial X 0.4, final X, X1 0.4, X2 0.7. Okay, so our middle conversion, titik tengah di antara 0.4 and 0.7, kalau kamu kira the middle X is 0.55. So middle X ni yang kadang-kadang student akan jadi confused nak kira. Kamu ingat je titik tengah antara X1 kepada X2 ataupun middle X antara X1 kepada X2. So it's 0.55. So then you find the difference. So the difference, kamu nak tengok difference kat depan, kamu nak tengok difference kat belakang pun tak apa. So kalau kamu nak tengok the difference at the front, so antara 0.4 to 0.55, the gap, how much is the gap? 0.15. Belakang pun sama. Berapa beza julat antara 0.55 to 0.7? Is still 0.15. So that's why delta X 0.15 divided by 3. Then you go to the 3 points. So become 1 per minus RA at my X1, which is 0.4. So apabila 0.4, X1 saya 0.4, minus RA saya 0.32. Done. Okay, next. 4 per minus RA at my middle X. Middle X saya 0.55 kan? So ia menjadi minus RA when my X 0.55. Okay, so part ni yang susah sikit sebab if you realize dalam table tak ada 0.55. Okay, so actually this question saya kena ubah sikit. Okay, in this question what I do is I interpolate antara 0.5 to 0.6 to get the minus RA at 0.55. However, actually this one is actually, saya lupa nak ubah dah soalan ni. Technically, it's not wise to interpolate sebab this is not a linear correlation. Maksudnya bila saya interpolate kan, saya interpolate pada 0.55 ni, minus RA dia saya dapat dalam 0.21. Actually, it's not so accurate sebab dia bukan linear punya line, bukan straight line. So bila kita bukan straight line, kita interpolate titik tengah tu dia tak accurate. Okay, so but don't worry, if ever this come out, this will not come in test and exam. Saya dah ubah tapi dalam note ni saya lupa nak ubah. I will make sure that you don't need to interpolate. Value tu akan ada terus, kamu tengok je daripada plot ataupun daripada table. Okay, but in this case, I interpolated and I get at my X 0.55, my minus RA is 0.21. Okay, plus 1 per minus RA at X2. So X2 saya 0.7, my minus RA is 0.12. So when you recalculate, you get your volume of your second PFR as 0.61. So what does it mean? Meaning, if I have two reactors in series, of which first reactor achieve 40%, second reactor 70% conversion, I need the volume of reactor minimal. This is minimal volume tau. Reactor saya kena sekurang-kurangnya sebesar 0.4 for the first one and 0.61 for the second one. Okay, next, let us do kalau kita guna 1 PFR terus. So kalau 1 PFR straight away means straight away achieve 0.7 using one single PFR. So I'm integrating from 0 to 0.7 pula. Okay, so maksudnya equals to FA0 delta X per 3. So again, case ni kita tengok balik delta X dia. Okay, so initial 0, final 0.7 sebab dalam satu single ni dia terus capai 0.7 dalam reaktor dia. So berapa volume diperlukan? Okay, so the middle conversion jadi 0.35 lah because initial 0, final 0.7, your middle conversion 0.35. And then you find the difference. So the difference either front or back is still the same. The difference will still be 0.35. 0 to 0.35, beza dia 0.35. 0.35 to 0.7, the difference is still 0.35. So delta X 0.35 divided by 3. In bracket, 3 points. So the first point is 1 per minus RA when my X is 0 plus 4 per minus RA at my middle X which is 0.35. So sama je dalam kes ni. By right, kamu kena interpolate. But as I told you, kalau test exam pun, saya make sure kamu tak payah interpolate because actually it's not so accurate as this is not a straight line. Okay, but in this case, just because it happened, kita interpolate, you get the minus RA at 0.35 as 0.345. Okay, plus 1 per minus RA and my final conversion which is 0.7 which is 0.12. So you calculate, you get the volume 1.03. Okay, so I will raise again the same question macam tadi CSTR. Tadi CSTR we realize to achieve the same conversion, you can actually use two smaller CSTR in series to achieve the same conversion, and these two total volume are smaller than using one single CSTR. However, what about PFR? Kalau kamu perasan, if I use two in series, total volume dia 1.01. If I use one single PFR is 1.03, hampir sama sebenarnya. So you might wonder kenapa dalam PFR dia hampir sama volume tapi kalau CSTR jauh kan? Kenapa? Tengok balik the Levenspiel plot. So kalau kamu ingat Levenspiel plot kan volume PFR equals to area under the curve. So kalau single PFR, the calculated volume is the area of this curve 1.03. If you realize, kalau I break it down into two PFR in series pun, that one that you calculated, 0.4 and the 0.61, is actually technically the same volume. Beza dia pun sebab tadi kita interpolate, so dia jadi tak accurate sebab tu je sebenarnya. Tapi theoretically, for PFR, either you're using one single PFR or using two PFR in series, sebenarnya total volume yang diperlukan adalah sama. But the same application like what I explained previously can be used. Means, let's say kamu tak ada one single reactor of a 1.03 dm cube, you can still run the reaction using two smaller reactor but connected in series. Means if you have two smaller PFR, you can still actually run the reaction in comparison to menggunakan one single PFR. Tapi you have to understand susunan reaktor tu. Maksudnya katakanlah kamu ada dua reaktor 0.4, 0.6. Kamu kena make sure yang 0.4 tu reaktor pertama, reaktor kedua tu 0.6. If you switch, you will not get the same conversion. You will not get the same outcome tau. So you have to understand, katakan kamu ada dua reaktor 0.4, 0.6. Katakan kamu letak reaktor pertama 0.6, reaktor kedua 0.5, 0.4, you will not get this, you will not get the conversion 70%. It must be exactly 0.4 kat depan, 0.6 yang kat belakang. Sebab it really depends on the conversion. Kamu tukar susunan, conversion tu akan dah tak capai like what you desired. Okay, so that's the discussion about this. Right, so next I will go to next part. Means now we already done on reactor in series. Habis. Okay, so we will go to the next part, very little part on space, time and space velocity, which you will see this a lot later in your lab as well. We will talk about space time, we will talk about residence time, so on and so forth. But first, fahamkan dulu apa itu maksud space time. Okay, first thing first, when we say about space time or space velocity, this is for continuous system. Kalau batch reactor, kamu perasan saya tak cakap lagi pasal batch reactor kan? Okay, untuk batch reactor, we always talk about reaction time. T, small t is reaction time. Untuk space time, residence time is for flow reactors, meaning CSTR, PFR. Bila kita cakap pasal time, kita cakap pasal space time, residence time. Kedua-dua ni akan menggunakan simbol tau. Okay, so it's different. T, reaction time, space-time, residence time, kita guna simbol tau as shown here on the formula. So difference so nanti kamu jangan confuse. Nanti kamu tengok tau, kamu ingat tu untuk PFR, CSTR, reaction time only for batch. Okay, next. Apa tu space-time? Okay, so space-time is time required to process one reactor volume of fluid based on the reactor entrance condition. Okay, Ini adalah beza utama antara space-time and residence time, which I will explain later. Space-time is we calculate using the reactor entrance condition ataupun condition reactors, conditions semasa dia masuk ke dalam reactor. Okay, apa tu condition dia? Okay, dia adalah obtained by dividing reactor volume. So of course entrance condition reactor volume masih sama kan, volume kamu asal ke, tengah ke, akhir. Reaktor volume saya tak berubah sebab isi padu reaktor saya tak akan mengembang, mengecut, pecah, dia tak akan berlaku. So reaktor volume sama. Tapi next, dia kata divide dengan volumetric flow rate into the reactor, epsilon naught, ataupun saya guna V naught. Sama je volumetric flow rate. So maksudnya entrance condition ni refers to the entrance volumetric flow rate, the inlet volumetric flow rate. So kalau kamu kira berdasarkan inlet volumetric flow rate, maknanya volume kamu bagi dengan inlet volumetric flow rate, dia menjadi space time. Okay, ataupun kadang kita panggil holding time ataupun kita panggil mean residence time. Apa tu maksud dia? Kalau mungkin kamu tak faham lagi, in a simpler word, okay, kamu ingat dia adalah continuous kan? Continuous system dia kan flow in, flow out, flow in, flow out. Okay. How long kamu nak tahan molekul tu dalam reaktor kamu sebelum dia mengalir keluar? That is your space time. Easy nak cakap? Easiest way to understand how long, sebab dia adalah flow, dia akan selesai mengalir keluar, mengalir masuk. Flow in, flow out. But there are certain time, ada masa yang kamu boleh tahan molekul itu dalam reaktor sebelum kamu paksa dia keluar. Masa yang kamu tahan tu adalah space time. Kalau kamu kira berdasarkan inlet volumetric flow rate. Okay, so kenapa ada kalau? Kenapa ada? Why I have a if there? Okay. Then, nanti saya akan explain kejap lagi. Saya explain dulu space time. I will explain that part a little bit while later. Okay, now. Space time, okay, time takes for the fluid to enter the reactor completely is the space time, ataupun this is another way to explain. Okay, consider kamu ada PFR ni, okay, kata PFR ni panjang kan, okay, katakan PFR ni dia punya length 20 meter, volume dia 4 liter, dia punya panjang tu 20 meter, okay, dia punya isi padu tu 4 liter. Okay, katakan kamu pump, kamu punya volumetric flow rate yang masuk tu 1 liter per second. Means every 1 second kamu pump in 1 liter air masuk ataupun fluid. Okay, so berapa dia punya space time? So space time dia menjadi 4 liter volume reactor divide by volumetric flow rate kan? 1. So you get 4 second. 4 liter bahagi dengan 1 liter per second. Before I forget, kalau space time, mestilah unit dia, mestilah dimension dia time kan? So unit dia mestilah time. Second, hour, day, minute. So kamu bayangkan 4 liter divided by volumetric flow rate, laju isi padu 1 liter per second, you get 4 second. Apa maksud 4 second tu? Okay, I explain in two ways. One way maksudnya, molekul tu akan tinggal dalam reaktor tu 4 saat je. Lepas 4 saat dia keluar. Lepas 4 saat dia keluar. So 4 saat je kamu tahan molekul tu dalam reaktor. Or another way to explain, volume reaktor, panjang reaktor ni 20 meter kan. Molekul tu hanya ambil masa 4 saat untuk bergerak from front to the back. 20 meter tu, dia merentas tu 4 saat dia dah keluar. So that's how you explain space time in a very simple way. Sebab continuous system itu cabaran dia. Dia sentiasa flow in, flow out. So kamu kena control berapa banyak masa kamu nak dia tinggal sebelum dia flow out. Okay. So if you might ask, habis kalau terlalu cepat macam mana? You worry that the reaction might not occur, right? Because it's too fast kan? 4 saat kan? You worry if they stay too short, dia tak sempat bertindak balas, dia dah keluar. So apa yang kita boleh buat? Of course, kita boleh slowkanlah flow rate. Kamu bayangkan kalau kita slowkan flow rate, okay. Kalau kamu tengok sini, matematik kan? Okay, space time ni berkadar langsung dengan volume, berkadar songsang dengan volumetric flow rate. Space time increase with volume, decrease with volumetric flow rate. Volumetric flow rate kena menurun, space time akan naik. So katakan kalau kamu kata 4 saat tu terlalu singkat. So what you do? You slow down the flow rate. So kalau kamu slow down the flow rate, logically molekul kita akan bergerak lebih perlahan kan. So kalau molekul kita bergerak lebih perlahan, space time akan naik. So means you make the molecule stay longer. So instead of 4 second, if you slow down the flow rate, katakan you slow down the flow rate. Katakan tadi volumetric flow rate 1 liter per second, kamu slow down jadi 0.5 liter per second. So kalau kamu kira space time 4 divided by 0.5, you get 8 second. So now space time dia jadi 8 saat. Means tadi 4 saat terlalu cepat, kamu slowkan flow rate, space time jadi 8 saat. Dia means dia tinggal lebih lama sikit, dia tinggal 8 saat sebelum dia mengalir keluar. So that's the concept of space time. However, now I go to the residence time. Okay, so you are probably quite familiar with residence time. Pernah dengar, tapi mungkin kamu confused apa beza space time dengan residence time. Okay. Reaction time saya dah explain kan, reaction time yang pasal batch. Okay, reaction time pasal batch. Okay. So apa beza space time dengan residence time adalah dia akan menjadi, katakan space time ni we calculate based on the initial volumetric flow rate. Flow rate yang kamu pump tu, yang kamu set dalam sistem, katakan nanti in the lab next week you will see, you will set the volumetric flow rate, no? You will adjust the flow rate. Let's say you adjust 1 liter per second, let's say kan. So you use that to calculate, that is your space time. Okay. So tetapi masalahnya volumetric flow rate ni will fluctuate during the reaction. Nanti minggu depan kamu tengok, memang kamu akan tengok flow rate, bacaan flow rate tu, although you set at 1 liter per second, dalam lab kita lain, dalam lab kita set dalam 200 ml per minute. Okay, let's say kamu set memang 200 ml per minute, tapi kamu baca reading tu, dia akan fluctuate 205, 210, then turun 197, 195, so on and so forth. So flow rate tu takkan stay constant. So if you calculate based on that, yang initial kamu set tu dia menjadi space time. Tetapi kalau kamu calculate berdasarkan the real volumetric flow rate during the reaction, during the process, that becomes residence time. Okay, ataupun kita kata tu adalah actual time or the average time the molecule really spends in the reactor. Space time tu berdasarkan entrance condition yang berdasarkan kamu set, tetapi disebabkan the changes of the volumetric flow rate and you calculate based on that real volumetric flow rate, you will get residence time. Okay, sebab tu dia kata if the volume does not change and the volumetric flow rate remain constant, residence time sama dengan space time. However, if there is a disturbance in the reactor, change in pressure, change in temperature, so on and so forth, therefore residence time tak sama dengan space time. Sebab tu nanti dalam lab report, kamu tengok, kamu akan kira berdasarkan bacaan yang sebenar. Sebab tu dia menjadi residence time. Kalau kamu kira berdasarkan yang original yang kamu set, that becomes space time. Done on residence time and space time. Okay, now we go to last one, space velocity. Okay, so apa tu space velocity? Okay, kalau space time, kita guna tau. Space velocity, simbol dia first of all SV. Space time tau, space velocity SV. Saya faham, banyak sangat simbol kan reaction ni, got a lot of symbol. So at this moment, if you find it very a lot, it's really understandable. But as you go on, probably you will see sama je benda tu kemudiannya. Okay, so apa tu space velocity? Space velocity basically sama dengan 1 per space time, 1 per tau. So kalau tadi tau, time, dia punya dimension time, right? Unit dia second, minute, hour. Kalau space velocity, kamu bahagikan saja, reciprocal kan, 1 per space time, 1 per tau. So unit dia become per second, per hour, per day, per minute, so on and so on. However, space velocity ni ada sikit susah untuk kamu nak measure or for you to calculate because dia mesti calculate based on a very specific condition. Okay, apa maksud dia? Okay, maksudnya sini, volumetric flow rate tu sebab kan kalau tadi space time, volume per volumetric flow rate kan. So kalau space velocity dia reciprocal, so become initial volumetric flow rate per volume. Terbalikkan saja. Tadi saya kata kalau space time, kita kira je pada entrance condition untuk inlet volumetric flow rate. However, for space velocity, inlet volumetric flow rate ni, you have to measure at very standard condition and it is different for gas and liquid, gas or liquid. Maksudnya kalau liquid, you have to measure the inlet volumetric flow rate at the range temperature between 15.6 to 23.9. However, kalau untuk gas, okay, untuk kira space velocity tu, volumetric flow rate ni, initial volumetric flow rate ni, kamu kena kira based on standard temperature and pressure, which is usually 0 Celsius 1 bar. Means kalau kamu nak kira space velocity, kamu punya tu adalah gas, kamu kena kira inlet volumetric flow rate tu apabila keadaan dia adalah 0 Celsius dengan pressure 1 bar. So it's a bit complex, right, to calculate the space velocity. Okay, so that's a bit the complexity when you want to calculate space velocity for your reaction in comparison to space-time. Okay, next. To differentiate or to really understand apa beza dia space velocity dengan space-time. Okay, katakan if you calculate your space velocity adalah 5 per hour. Unit dia jadi per time, per hour, per second. Katakan kamu kira space velocity tu kamu dapat 5 per hour. Maksudnya, for every 1 hour, you will actually process 5 reactor volume. Okay, kamu bayangkan tadi yang PFR yang panjang tu kan saya kata dia ambil masa katakan 4 saat untuk merentas. Okay. Kalau katakan kamu kira kamu dapat 4 per hour, apa maksud dia? So means for every hour, 4 kali lintasan tu berlaku for every 1 hour. Means 1 hour, there are 4 times of that occurring at same time. Occurring at that 1 hour. 4 kali benda tu berlaku untuk setiap 1 jam. But if they say space time tu 5 minit, okay, katakan space time tu 4 minit, maksudnya 4 minit lah. Maknanya how long it takes? 4 minit to across the reactor. 4 per minute means for every 1 minute, 4 kali benda tu akan berlaku. 4 times the molecule, 4 different molecules will across the reactor in every minute. Something like that. Okay, so that's the difference between space velocity and space time. Okay, right. So we already concluded chapter 2, but we still have about half an hour. So I will actually continue to chapter 3 a little bit, just a little bit on the chapter 3. But I will give you about 1 minute break. Okay, we have about 1 minute break, then we will come back for continuation of chapter 3. I will just enter a little bit